Welcome to the next video in this series of short introductions on the atom and its structure. In the previous video in this series, linked in the description below, we saw how earlier experiments in the 20th century led to the development of the theory of quantum numbers. There were four quantum numbers that are developed: n, l, m subscript l, or m sub l, and m subscript s. N, the principal quantum number, gives you the energy level of the atom, of the electron rather, and can have any positive integer. This is essentially the distance between the electron and the nucleus, creating a potential energy. That potential has to be balanced with kinetic energy. That is done through orbits, or angular momentum, which are defined by the quantum number L. L is related to n as the amount of energy is related to the distance to the nucleus, and L can have any integer values from 0 up to n-1. Once orbits are established and they have shape, that means there's also going to be direction involved. The third quantum number, m sub L, is called the magnetic quantum number. It essentially gives the direction of each of the individual suborbits or orbitals relative to the nucleus, and as such, it is related to L and can have any integer values from negative L to positive L. Finally, the last motion an electron can do is spin. This is the simplest motion, as it can either go clockwise or counterclockwise, leading to numbers plus a half or minus a half. These relationships may be complicated, but they do wind up explaining the periodic table because of something called the Pauli exclusion principle. Essentially, the four quantum numbers give an address for an electron in space. Since two things cannot be in the same place at the same time, no two electrons can have the same four quantum numbers. Relates to the periodic table as follows. If you look at a set of quantum numbers in detail, the lowest possible value you can have for n is 1. L can have any value from 0 to n-1, which leaves you with a value of 0. M sub L, depending on L, from negative 0 to positive 0, again, is only 0. And spin can either be plus a half, giving a set of numbers 1, 0, 0, plus a half, or minus a half, giving 1, 0, 0, minus a half. If you look at the periodic table, n equals 1 has only two possible values. On the periodic table, the first row only has two elements. Moving on, the second possible primary quantum number is 2. If n is 2, L can either be 0 or L can be 1. In order, if L is 0, m sub L can only be 0, with spin being plus a half and minus a half gives you 2, 0, 0, plus a half, or 2, 0, 0, minus a half. If L is 1, m sub L can be any values from plus 1 to negative 1, or plus 1, 0, and minus 1. Again, each of these can have spin values of plus or minus a half, giving sets of numbers equal to 2, 1, plus 1, plus a half, 2, 1, 1, minus a half, 2, 1, 0, plus or minus a half, 2, 1, minus 1, plus or minus a half. In the case where n equals 2, you will note that there are 8 possible combinations of quantum numbers that can be achieved without repeating. There are also 8 elements in row number 2. Therefore, the rows on the periodic table correspond to the individual energy levels of the highest electron, or the last electron added. Looking further, so the rows would be n equals 1 through 7. Moving on to the next quantum number, L. You will note, no matter what n is, the value of L can only give two possible quantum numbers. Sets of quantum numbers, rather. You will also notice on the left-hand side of the periodic table, there are only two columns sticking up. L equals 0 corresponds to an s orbit, and those are the orbits being filled in the first two columns of the periodic table. Similarly, if L is 1, regardless of the value of n, there are 6 combinations. And if you look on the right side of the periodic table, there are 6 columns that are sticking up. So the p orbits are being filled in on the right side of the periodic. Essentially, for any periodic table, the energy level is given in the rows. L defines the orbit from 0 to n minus 1. The common orbits, L equals 0 is an s orbit, L equals 1 is a p orbit, L equals 2 is a d orbit, and L equals 3 is an f orbit. M sub L can be from negative L to positive L, so an s orbit has one value of m sub L. A p orbit with L equals 1 has 3 values of m sub L, negative 1, 0, plus 1. D orbit at L equals 2, m sub L has 5 values from minus 2 to plus 2, and an f orbit at L equals 3 has 7 values from minus 3 to plus 3. However, the final value, the final quantum number, spin, can only have 2 values. Therefore, according to the Pauli exclusion principle, each orbital defined by m sub L can only hold 2 electrons. If one looks at the periodic table, knowing this, the s orbital has a single orbit and therefore can hold 2 electrons. That comprises the first 2 columns of the periodic table, where the first column is filling in the first s electron and the second column is filling in the second one. A p orbit with 3 orbitals from negative 1 to positive 1 can hold 6 electrons, corresponding to the 6 columns on the right side of the periodic table, P1 through 6, 1, 2, 3, 4, 5, 6. The d orbit at L equals 2 can have 5 possible m sub L's, 5 possible orbitals, 10 electrons. Noting the center of the periodic table where the dip is, there are 10 columns. Each one corresponds to adding an additional d electron. And finally, at L equals 3, the f orbit has 7 orbitals, which means it holds 14 electrons, corresponding to the 14 columns that are set outside the periodic table. So the periodic table is essentially laid out as an electron map. Each box corresponds to adding 1 proton and 1 electron, where each electron going into a specific location. You can read this quite simply, starting with the simplest element, hydrogen. Hydrogen is in row 1, column 1, which means its single electron is in the 1s1 orbit. If one goes further to nitrogen, nitrogen has 7 electrons, being the 7th element. Starting from the beginning, you fill in 1s2. You're now in the second row, where you have to go through elements 3 and 4, 2s2, and 3 columns over in the p side to give you nitrogen being 1s2, 2s2, 2p3. Oxygen next to nitrogen is going to have all of nitrogen's electron plus an additional electron at 2p4. Fluorine, again, is going to be 1s2, 2s2, and one box over, 2p5. Neon is 1s2, 2s2, one more box is 2p6. Sodium. One is now moving down to the third row. So sodium would have all of the preceding 10 electrons, 1s2, 2s2, 2p6, 3s1. Magnesium would have those 10 electrons again, 1s2, 2s2, 2p6, 3s2. You can continue on this way through the entire periodic table, which will admittedly get rather long and rather tedious. However, one can continue and notice something very. You can have an abbreviated electron configuration. Noticing neon in the final row closes out the second row at 1s2, 2s2, 2p6. Sodium and magnesium have all of those same electrons plus additional ones. So you can simply abbreviate the electron configuration based on group 8, which are called the noble gases. These gases, helium, neon, argon, krypton, and xenon, end a row. They close out what is called an electron shell. Therefore, they are going to be unreactive. They do not want to give away electrons or accept electrons. They're extremely stable and essentially known. So instead of writing sodium as 1s2, 2s2, 2p6, 3s1, you'll note it's one past neon, so it's simply going to be neon 3s1. Magnesium would be neon 3s2. A point that may be noticed, helium seems to be in the wrong place. Helium is 1s2, but it is all the way over on the right. The reason for this is that it is the first of the noble gases. It closes out that first shell, so it is placed reactively with the other noble gases. So again, abbreviations possible, where nitrogen becomes helium 2s2, 2p3, oxygen 2s2, 2p4, fluorine 2s2, 2p5. If I take any other random number, calcium in the fourth row. The previous noble gas is argon. I am now in the fourth row, 2 electrons over, so calcium becomes argon 4s2. Sulfur. You look at the periodic table, you note neon is the next noble gas. Sulfur is in the third row, passes 3s1, 3s2, and then fills in 4 of the p orbits. So that would be, sulfur would be neon 3s2, 3p4. So far, we've only looked at the ends. Special case occurs in the middle, in what are called the transition elements, where the d electrons are being distributed. In order to see what happens here, you have to go back to the original model of the atom. The electrons are set in various shells or distances from the nucleus, n equals 1, 2, 3, 4, where that distance provides a potential energy inversely proportional to the radius. If one looks and plots the radius of an electron in terms of its primary quantum number n versus the inverse of the energy, the lowest energy, the easiest electrons to fill are going to be from the bottom up. So you'd fill in the 1s level, followed by the 2s, 2p, 3s, 3p, and so on. These are the energy levels available. However, if you look at the y-axis, you'll note if I'm filling from the bottom up, there's a crossover at the larger elements between the s level and the d. The 4s is actually at a lower level energy than the 3d. 5s is at a lower energy than 4d. So when one starts filling in electrons, they will fill in from 1s to 2s to 2p to 3s to 3p quite simply. After that, they'll jump over to the 4s level as the next lowest before proceeding to the 3d level. Additionally, after the 3d, they'll go back to the next highest level, 4p, where for their journey, they wind up at 5s before landing on 4d. This leads to the periodic table. If I take an element, manganese, the last noble gas is argon. It is in the fourth row. Counting boxes, one would expect 4s2, and the fifth box in should be 45, but the D level is always one behind, so it becomes 3d5. For a similar reason, I can pick up any other element I want. Tin. I now have to go through the transition metals. Tin starts at krypton, fifth row, 5s2, but since it's 5s, I now have to travel through 4d10 before coming back up to 4p and 2 boxes over to 4p2. So the transition elements, when filling in the electrons, are always going to be one row behind. Additionally, if one looks on the bottom of the periodic table, separated are 14 columns. These are called the lanthanides and the actinides based on the first element in each of those rows. Looking carefully at a periodic table, row 6 starts with element 55, followed by 56, followed by 57, followed by 72. Obviously, something's missing. The thing that's missing are the 14 numbers between 57 and 72. Similarly, in the 7th row, 87, 88, 89 jumps to 104. In both cases, those quote-unquote missing elements are found separated on the bottom of the periodic table. So elements 58 through 71 and 90 through 103 are found at the bottom. The reason for this is simply convenience. The periodic table is a flat piece of paper, and it would need to be a three-dimensional shape to accommodate the f orbitals. Because similar reasoning why the D level is one row behind, the F level is always going to be 2 rows behind. So if I pick a given element, actinium is going to be radon, 7th row, 7s2, 61. If I go past actinium to uranium, which is element 92, I am still at radon, 7s2, 61, but now I drop down to the bottom. There are 3 F electrons, and they're going to be 2 rows behind, so uranium is 7s2, 61, 5f3. Similarly, if I go all the way across to lead, the previous noble gas is xenon. I'm now in the sixth row, 6s2. After the sixth row, I drop down. I have to fill in all 14 F electrons. So it's 6s to 4f14. Back up to the D level, which is 5d10. And finally, back over to get to element 82, which is going to be in the P level, 6p2. So essentially, the quantum numbers give the shape of the periodic table. And once one knows the shape of the periodic table, one can then determine what the electron configuration of each individual element is. In the following video in this series, you'll find out how you can use that information to determine the reactivity of any given element.